Good morning, everyone. My name is Jean-Marc Zaccardi from IFPEN. I am coordinating and introducing today the main achievements of the EAGLE project. So EAGLE stands for Efficient Additivated Gasoline Lean Engine. So some general information to start my presentation. We started our activity in 2016, and actually we are completing our project today. Our consortium is made of 9 partners from 4 different countries, as you can see on the right side of your screen, for a total EU funding of around 6 million euro and a total effort of around 500 person months. So just like some other projects such as Paragen or Upgrade, EAGLE was granted under the GV02 call in 2016 as a research and innovation action. And we are addressing the second impact of this call, which is future combustion engines for electrified powertrains. Considering as main objectives a long-term fleet target of less than 50 grams of CO2 per kilometer, PN emissions down to 10 nanometer, and Euro 6 NOx emissions without any conformity factor. In our case, the final demonstrator is not a vehicle. This is a multi-cylinder engine at the test bench. This engine that you can see on the right side of your screen is relying on several technologies and especially on lean mixtures, diluted combustion. So unfortunately today, given the time limitation for this presentation, I cannot show you all of our results, so I will focus mostly on engine efficiency. For this talk today, I've selected 2 main technologies for which I will show you our main achievements. The first one is related to the ignition system, because when it comes to diluted combustion with high air-to-fuel ratio, preferably you should use a kind of space ignition technology to improve the ignition performance. So in our case, we've selected an active pre-chamber. So inside this pre-chamber, you will find a fuel injector and a spark plug. And basically the idea is to ignite the mixture inside the small pre-chamber volume, and then the jets coming out from the holes of the pre-chamber will ignite the highly diluted mixture in the main chamber. This is not a new concept. This is already used in very large bore engines, but the main challenge in our case was to adapt this concept to adapt and optimize this concept to a small bore gasoline engine. So regarding the main achievements, several investigations have been conducted from 0D simulations up to optical diagnostics, as you can see here. Unfortunately, I cannot show you all these results, but you will find many more details in our previous publications and also in upcoming publications for 2021. In the end, we could successfully implement the pre-chamber ignition system in different small bore engines down to 76 millimeter bore. We could also demonstrate that a stable combustion process is possible in various conditions, and even with air-to-fuel dilution ratios quite above 2, which was the initial target. And we've also shown that the pre-chamber ignition system is compatible with different fuels. So you can use it obviously with liquid gasoline, but you can also use it with CNG or even with hydrogen. In the end, we could also show that very high indicated efficiencies can be obtained with an active pre-chamber. So not only with an active pre-chamber, but also with an optimized combustion system. I mean the charge motion, the compression ratio, for example, and also the valve train actuation strategy. Here you can see some examples in very specific conditions, but I would say that the main takeaway of this slide is that you can achieve more than 48% thermal efficiency when combining an active pre-chamber with an optimized engine concept. In parallel to the pre-chamber, we've also investigated hydrogen boosting. So here the idea is not to use hydrogen as a single fuel, but as a supplemental fuel, which means together with a classical gasoline fuel. The idea is to benefit from the properties of hydrogen to extend the dilution limit. So as you, I think all can see now, new initiatives are launched or announced daily around hydrogen, which I think opens also a few doors for new applications of hydrogen, also in ICE-based powertrains. In our case, in the Eagle project, we could show that when combined with E10 fuel, even a small amount of hydrogen can significantly increase the dilution limit. You can reach also here, as you can see, an air-fuel ratio of 2 without any pre-chamber, lowering the NOx emissions and also increasing significantly the efficiency. I think when it comes to NOx emissions, that with a proper amount of hydrogen and optimized engine configuration and settings, it should be even possible to lower the NOx emissions below 10 ppm, so single-digit NOx concentration at the engine outlet, which would be a significant improvement in terms of pollutant emissions, at least for some operating conditions. So as I mentioned during the introduction, I cannot show you our final results since we are completing the project today. I will deliver the final deliverables later today after the presentation, and we will first discuss the final results with INEA during the final project review. And I think that some public information will be disclosed later in 2021. But however, I can give you some hints about what we did for the final multi-cylinder engine. First of all, we have implemented a dual-stage turbocharging system using a low-pressure turbocharger and an e-charger. So this is an electrified turbocharging system. We found out that given the requirements of the Eagle application, that would be the optimal solution, but of course, you can consider various turbocharging configurations. Most likely, if your target is to achieve ultra-lean combustion over the complete engine map, then you will have to use a dual-stage turbocharging system. And when it comes to dual-stage turbocharging system, one of the key points is to optimize the power split ratio between the high-pressure compression and the low-pressure compression stage, because whatever the architecture you are considering, you will have to find an optimal value for this power split ratio. For example, in our case, the e-charger obviously is run with electricity, and this electricity is not given for free. So you have to take into account this electricity production in the overall energy efficiency assessment of the engine and of the vehicle. In parallel to that, we've also developed a closed loop combustion control strategy. So basically, we are using in-cylinder pressure sensors to monitor the combustion stability in all the cylinders of the engine. And then we can not only monitor the stability, but also act on the injection and ignition settings inside the pre-chamber to optimize the combustion stability for all the cylinders, and consequently to lower the pollutant emissions and to increase the brake thermal efficiency. For the final demonstration, at the test bench, at the engine test bench, we also evaluated a complete after-treatment system, including a DOC and a GPF, and also a newly developed LNT by our partners. Today, for this speech, I would like to highlight that not only the NOx regeneration efficiency has been taken into account, but also the selectivity of the LNT towards ammonia and towards N2O. Keeping in mind the future potential regulations. And you can see here on this example that the material combinations that have been selected for the Eagle applications are better than the reference in terms of NH3 and N2O selectivity, better than the reference, which is a serial production LNT. So the main impact in the end of the Eagle project is that we have demonstrated that ultra-lean SI engines could be a solution to reduce the impacts of future hybrid powertrains. So in terms of local pollution, but also in terms of CO2 emissions. Focusing on the efficiency, if you look at the efficiencies that you can expect with a ultra-lean engine used in a multi-mode hybrid powertrains, then you can achieve less than 50 grams of CO2 per kilometer for a PHEV application. For your information, the hybrid powertrain that we are considering in the Eagle project is directly derived from the E-Tech configuration from Renault. The situation would be a little bit more difficult for HEV applications, for which we could achieve somewhere in between 85 and 90 grams of CO2 per kilometer. New models, methodologies, and technologies have been developed also during this project and are now available to further improve the engine efficiency. For your information, I cannot show you those results today, but we have measured PN emissions down to 10 nanometer with 2 different devices. And now if we look into the future and at the next steps, I would say that the first one would be to define more clearly the roadmap towards higher TRL for serial application, considering specifically the engine complexity. And we should also demonstrate the ultimate compliance of this engine concept with current and future regulations, namely with Euro 7 and RDE regulations. With that, I can conclude my talk today. Thank you very much for your attention. I hope that you will enjoy this digital conference. I will be joining the live discussion at the end of the session, but if you have any question about this project, you can still use my email address that you will find on this slide. Thank you very much.